Hi everyone, I'm here today to present Starforge, StarTree's next gen cloud architecture for managing our StarTree Pinot deployments for our customers. I am Chris Kellogg. I'm a software engineer at StarTree working on cloud and platform services, and I'll be presenting with one of my colleagues who I'll let introduce himself.
Hello, all. I'm Krishna. I've been with StarTree for about 3 years. I work alongside Chris on the cloud team, and we developed Starforge along with a few of our other colleagues.
So I will sort of give an overview of sort of what we're going to present today. I'll give a sort of brief overview on StarTree and kind of what we work on, and then I'll sort of go into our next generation cloud architecture, and then we'll talk about some of the challenges that we had before, and then some of the challenges we've had working on this new architecture. And then sort of at the end, we'll kind of walk through some of our uh, solutions and in a way and sort of how we solve some of the challenges. So I'll start with sort of a quick overview of StarTree and sort of what we do. So StarTree, we're a company that works on a open source Apache project, which is Apache Pinot. It's a real-time analytics database that came out of LinkedIn. What we do is we offer managed services of Apache Pinot for our customers in sort of various different deployment models. So on to the sort of this next slide. So what we sort of offer is we offer this managed service, and we offer it in a variety of different deployment models. And so one is BYOC, which stands for Bring Your Own Cloud. Another is dedicated SaaS, which is similar to BYOC. Another one is multi-tenant SaaS. And then we have another one, which is what's called BYOK, which is um, sort of bring your own Kubernetes and run Apache Pinot. We also develop and work on all three of the different clouds, so Amazon, Azure, GCP, etc. That's sort of a brief overview, and so now I want to sort of get into this next generation architecture and kind of why we did it and sort of what it's about. So when we set out to design this next generation architecture, we had a few requirements that we wanted to do. One is we wanted to build a sort of single stack that could handle multiple different product offerings. So as we as we sort of work with our customers and sort of provide them the services that they need, we've sort of discovered we need to potentially package things in sort of different ways. So that's either a SaaS offering, a multi-tenant offering, a BYOC or a BYOK offering. And so we didn't want to build individual solutions for all of those. So we tried to come up with a way, can we build some single stack architecture that can support all of these different product offerings? So if something new comes in tomorrow or a different requirement, we don't have to sort of develop a lot of code or change things to support a new deployment model or offering for our customers. We also wanted, to provide fast iteration. So as new requirements come in, as things change, we're able to add and remove different features and things that the customer needs, as well as, it needed to be highly scalable to support tens, hundreds of clusters, thousands of clusters, across all the different clouds. It also needed to be sort of decoupled in a way where we're able to sort of modify or change things without affecting other pieces of the stack. And then also security was very important. And so one of the things we sort of discovered is, there are customers that are very secure, people are very secure conscious, and we sort of need to limit access to their clusters. We also need to be able to limit outbound access, and and be able to control um, who and what is accessing the cluster. And we'll sort of explain in the design of how we sort of handle that. So I want to start out at sort of a high level view of the our new architecture. And so you can see sort of in this diagram, there's sort of, I would say, like four major components, and we'll kind of drill down into some of those different areas as we go along. So at the top, we have this thing we call like a cloud portal. This is where people come and sort of interact and create their different types of environments, whether it's a SaaS, BOLC, it's how they do their different configuration for their where they want a deployment, what type of cloud, how they want to sort of scale or configure Pinot. Um, that sort of interacts with some of these underlying services that you see. And so we have these sort of support services that do configuration management. We have some services that does upgrade management, as well as we have secret management. And then we have this control plane, which is sort of the heart of all the architecture, which is sort of like the brain of everything. And so that offers some, APIs. It has this controller and it has this task management framework. We'll sort of dig in later on as well. And then we have these sort of infra as a service that sort of work and provision resources in the different cloud environments. And then we have this data plane agent framework that sort of runs in the customer's account or in our account, sort of outside of our control plane that actually uh, manages and deploys the Pinot deployments and software that the customers run and use. The cloud portal, someone comes and configures a Pinot environment. Underneath, that gets pieced together into these sort of individual entities that the control plane manages. And so the cloud portal works with this config service to sort of generate these entities. Then they send to the control plane. Once they're in the control plane, that's where all of the work and processing starts to happen. So as we sort of provision and bring up these environments for our customers. So if I kind of now sort of central dive into the control plane, I sort of talked about the entities. So we have this concept of these entities within this Cloud V2 design. And what these entities are is essentially a model that abstracts software and infrastructure. Um, and with these entities, we're able to provide this sort of modeling and relationship where things can get stitched together. And once they're stitched together and sent to the control plane, we have this controller. So we essentially form this DAG of these stitched together entities. And then we have this controller framework within the control plane that sort of monitors and watches these different entities and goes through a state machine process. And from that process, it decides when it needs to generate tasks to be worked on. And then we have this task framework management that sort of processes and manages the life cycle and of the different tasks. And I'll kind of sort of dive down into that in a couple slides. And then we also have this secret management. So we have this way where we can securely store credentials, and we have a pipeline where we can securely ship them down into the data plane for use. And then we also have access control, and so limited ways to generate access for people to access the cluster. So now I'm going to kind of dive into some of the modeling or the StarTree entities. So at a high level, we people come to the control plane, and at the control plane level or sort of this product level, is you think in accounts, organizations, deployments, projects. I want these pieces of software to run. And so this diagram kind of shows you how we sort of think at the product level or at the control plane level, how do we configure this. And so what the portal does is sort of deals with this product level pieces and at the end of the day, what it does is it maps these different concepts into these logical entities that the control plane understands and can work on. So this is an example of mapping, let's say, an environment into the cloud portal, mapping into a DAG. And so as you can see here, we have different entities that we sort of need to create for an environment for a customer. So if I kind of walk you through, it needs like an AWS account, and then we need a VPC, and then we need a Kubernetes cluster, and then we have this notion of cells where we deploy um, packages of software. So you can see within the cell we have Pinot, data portal, and some authorization, and then we also have storage. So what the control plane does is it knows it's creating this BYOC environment. It then creates these individual entities, sort of going through the config service, and it creates these relationships, and then it sends it to the control plane. Then within the control plane, there's a controller that works on there and then generates tasks based on if its dependencies have been completed, because within the framework, there's outputs of sort of the parent relationship that are needed for the child relationship. And so the control plane and the task framework sort of handles all of this. So now I'll kind of dive into some of the key sort of aspects of this task framework. So I kind of mentioned um, every we have these sort of individual entities that can be stitched together into different deployment models, and they are sent to the control plane. Once they're sent to the control plane, we have this task framework that actually sort of does the work on these actual entities. And so um, within the control plane, we have these different services that work on these different entities. So as an example is we'll have a network service, a storage service, a Kubernetes service. These services will pull out to the control plane every so often, asking are there new tasks to work on. And tasks are generated from the control plane and the controller working inside. Once they've sort of gotten these tasks, they sort of go out and create the infrastructure in the cloud, and then they send back a status information. And then once those have been completed, the controller sort of recognizes and is able to schedule child job, sort of dependent jobs once the parents have been completed. So we built this sort of generic task framework and this sort of generic entity model where we can sort of stitch together or leave things out, different deployment models. So as customer needs change, or as we need to experiment or do a different deployment model, we can really just make configuration changes and just stitch these entities together, as opposed to going out and having to make significant code changes. Um, so now I'm going to pass it off to Krishna, and he's going to kind of walk you through a little more of the architecture, and then kind of talk about our challenges and solutions.
Thank you, Chris, for walking us through the control plane and the task framework. Now, let's dive deeper into data plane. The data plane is composed of multiple interconnected components, each handling a specific responsibility to ensure that the platform runs smoothly, securely, and reliably. Now, we'll walk through a few of the components and the features that we currently have inside the data plane. First off, we'll start with the Uber agent, which acts as a central coordination point within the data plane. Its job is to retrieve the latest cluster specifications from the control plane and distribute them to all the cell agents. You can think of it as a command relay, which ensures that every part of the system knows what it needs to do and it stays aligned with the desired state as defined inside the control plane. So one of the other features of Uber Agent is in regards to the status pipeline. While the Uber agent pushes instructions downstream, the status pipeline feature works in the other direction. It pulls health metrics and status updates from the components and channels them back to the control plane through the Uber agent. Using this continuous feedback loop, it ensures that we have real-time visibility into component health and performance, helping proactively address any issues before they escalate. Next, it's the cell agent. Once the Uber agent distributes the specifications, the cell agent takes over locally. The cell agent is responsible for actually executing those instructions, creating, updating, and managing components as per the cluster specifications that it received from Uber agent. Each cell agent has a few namespaces that it controls, and all of the components running in those namespaces are managed by it. It ensures that the desired state, which is set inside the control plane, is released and is like running in the cluster. This means that all of the components are like fully decoupled, and then we can upgrade them individually without having any dependency concerns. Along with the cell agent, there's also like a bunch of StarTree suite apps and pods that are like running inside the cluster. These include like data manager, apps manager, and third eye, along with the Pinot control, um, the Pinot components, and the Pinot operator. These services provide the core platform functionality, from maintaining data to orchestrating applications, enforcing auth and role-based access control. The Pinot operator, which runs inside the cluster, takes care of all of the operations on Pinot components, like scaling them up, scaling them down based on the workload and the configuration provided. With all of these StarTree apps, it acts as a backbone for our platform services, which ensures security, compliance, and operational efficiency. I know in the previous slide we spoke about the status pipeline, but we also like have monitoring components that are like present inside the cluster, which complements the status pipeline. These tools collect metrics from the entire cluster, giving both the internal teams and also the customer a holistic view of the system health as well as performance. Using these metrics, it improves the operational transparency, optimizing performance, and planning for future growth. No platform is complete without any robust security controls. This includes how the secrets are handled, along with the TLS certs across the platform. By integrating these controls directly into the data plane, we ensure that the data in transit and at rest is secured, and all of the sensitive credentials are protected at all times. Next, we have the configuration management. This feature uses a template-based deployment specifications that flow through the agent hierarchy. This approach not only streamlines deployments, but also like ensures consistency across the environments and making it easier to manage large-scale clusters with confidence. Finally, we'll come to the operational workflows, where these are like structured processes that guide us on how upgrades and components are added into the cluster. By having all of these like well-defined workflows, we ensure that any changes to the system happen in a controlled and a repeatable manner. To wrap it up, the data plane is tightly coordinated, where each component plays a distinct yet interconnected role, from central coordination and real-time monitoring to robust security. And of course, these are just highlights, and each of its components has its own depth. Before we jump any further, let's take a moment to understand some of the challenges we are facing in managing these environments. The first major challenge is around operational changes. In any large-scale system, we are not dealing with a handful of components. We are talking about upgrading tens and thousands of custom clusters at a time. Whether it's rolling out new configurations, updating software versions, or making adjustments to the platform services. The scale here adds complexity. Coordinating and applying changes to tens and thousands of clusters while maintaining consistency and minimizing downtime is a non-trivial task. Next, we have challenges with the configuration management. Given the scale and diversity of the system, we need an easy and a reliable way to generate entity payloads. The configuration data that actually like defines how each component should behave. But it's just not about generating the configurations quickly, but also making sure we like persist them and maintain customizations over time. Different environments and customers and have different use cases, and we need a system that actually like preserves these customizations even as we like push broad updates. Without this, we risk overwriting local changes and leading to potential outages and misconfigurations. So how do we like plan on solving this? So we introduced a new service called config service, which is like at the center of our solution. The config service is a purpose-built service to simplify the management of Starforge entities at scale. Firstly, it uses templates to define and manage entities. These templates give a structured and a repeatable way to generate configurations. So instead of manually creating thousands of individual configurations, we simply define a template and reuse it. What's powerful here is that the config service doesn't just stop at templating. It also allows the UI to dynamically render inputs for each entity. This means that the users aren't hand-coding any JSONs. They just get a user-friendly interface that adapts based on template, making it much easier to manage configurations without needing any deep technical knowledge. Another critical feature is persisting customizations. You remember the challenge we spoke of earlier in the previous slide, where the updates could potentially wipe local changes. The config service ensures that the customizations made at the entity level are retained, and even during upgrades or bulk operations. So teams can like safely upgrade components without losing any tweaks or overrides. Once the templates are created and inputs are captured, the config service renders these templates into JSON payloads for the entities. It also like stores details of template usage, giving us a full visibility into which configuration was applied across the system or in a specific cluster. And using this, it helps us to enable bulk updates, whether we need to like push new versions of a component or roll out a broad policy changes. The config service allows us to do this efficiently and reliably. Coming to batch upgrades. Now we've like covered how we manage configurations and ensure like flexibility at scale. You know, they say you don't really understand scale until you try to push an update to a few thousands of clusters at once and hope they all listen. This is where a batch upgrade framework comes into play. We have designed this to be both flexible and safe, giving us full control over how upgrades are rolled across the clusters. First, the upgrades are entirely config driven. This means that the workflows themselves are defined in configuration and not hard coded, giving us the flexibility to adjust and tune the process as needed. We can upgrade the entire fleet to a target version in a controlled way, whether that's rolling out a critical patch or moving to a new major release. Safety is built at every stage. We run pre-flight checks before any upgrade begins, making sure that the environment is ready and all of its dependencies are in place. And once the upgrade completes, we perform post-upgrade validations to confirm that the system is in a healthy state and the upgrade was successful. To add an extra layer of caution, we have a preview mode. This allows us to simulate the upgrade plan without making any changes. So we can verify that the actions and anticipate any issues and plan safely. When it comes to execution, we have flexible options to suit different environments. We can adjust the batch size and also like control the level of parallelism, which means how many number of environments can be upgraded at any point in time and how many number of environments in parallel can we push this upgrade to. Error handling is also like pretty robust, and we support a fail fast mode so that whenever we first see any sign of trouble, we just like stop, or we can continue with the best effort mode to upgrade unaffected entities. To avoid wasting any time and resources, we have also built in smart skip capabilities where the system identifies and skips entities that are already at the desired version and the state, preventing any redundant work. Of course, tooling and monitoring is very important and very critical in these operations. Throughout the upgrade, we have real-time status updates, detailed logs, and live metrics to monitor the progress and quickly identify any issues. This level of observability means operators will have full confidence in the process, and then they can track any in-flight and upgrades and intervene if needed. So in overall, the batch upgrade framework gives us the flexibility to handle any large-scale changes and do it safely without risking the system stability. Thanks a lot for attending this talk. We are more than happy to answer any questions, or please join our Slack channel in case if you want to find out more about Starforge and all of its capabilities.